Okay, let's get started. Can you hear me? Good. Okay. So we'll continue what we did last time with more detail. First, we need to find the location of a central station. Oh, by the way, the example I give here, exactly the same things, okay? But so you can follow the handout I give you. I don't like to memorize, so I tend to just think along the way. You follow me? So I'm just create a new one. But they're all the same, okay? And why I'm only doing 4x4 because for limited time is easier. Oops, too big. Okay, I'll do it over here. Okay, so this time we do it based on assumption. What's that assumption? There is a place we call central station. So let's just say central station location at 101. Why 101? Well, because we say that's 101. Okay? If you don't like 101, you can have 201, doesn't matter. But that's just the location. We start measuring everything. 101. And then, of course, once we have the central location, okay, we need to have 4 treatment. Well, later we can have 10 treatment, 3 treatment. And then why only have 4 observation? Because I don't have enough money. I only can do 16 trials. If I have more time, more money, you can have more. But on the other hand, as a system engineer or engineering management, okay, if you can prove something useful, okay, me 200 trials, I can prove something useful, okay, 10 trials. Who is better? Me, right? So, in other words, is that if I can do something, here I'm using 16 trials to prove something. If I can use only 12 trials, or, as few trials as possible, that's the intelligence, okay? So now let's have treatment. And this time we just call treatment AA, AD, ZZ, WW, okay? And then say AA is above the central station by 15. Why by 15? Well, because the people there say we want to have a station above. And then there's another one is below 12. So everything below 12. So far so good, right? This is pretty much the same thing I did last time, except this time I do it deductive. Means that I said the world like this and go on, okay? Last time I'm just, okay. And then the next one, say, is above by 8. Okay? But remember, since that's the central station, that's the center. So need to average out. So in other words, the last number should equal to negative the sum of this 3. Oops. Why? Because if that one is the negative of this 3, what will be the sum of this 4 number together? What will be the sum of this 4 number?
Should be 0.
Nada, right? And why nada is important? Because you said it's a central station. It's the center of mass. If this is the center of mass, and here is a balance, I should have some weight over here, I should have some weight over here. But when all the ways going very, very far, getting very, very close, when it's balanced, should be what? I'm right in the middle, 0, right? So if I have, say I don't like this one is 15, give me a number.
17.
17. So if this guy is 17, see what happened to the last one. Need to push out to 13 in order to balance the whole thing. Make sense? Oops. Whatever I done. Okay, here we go. So let's get back to 15. Okay, and then, so this is the station location. Above 15, below 12, above 8, below 11. Make sense? Okay, so here is the way station. Or you can consider this is where the treatment going to be. Okay? And then next, I need to have some local commute. Okay? And the local commute really is some randomness. Okay? Or you can say random error. Okay? So for the random error, means that some travel above 15, a little more, a little less. So this time we will say that, hey, give me a random number, but this random number, I don't want to get it from uniform distribution. I'll get it from normal random distribution. So I'll say norm, inverse, and don't worry, I'll come back, tell you where we get that from, okay? But right now, just give me a random number from, average is always 0. Okay, the local commute, people look at this. What do you think is the local commute should be? Would the local commute more than 8 miles if the unit is 8? Probably not, right? Why? Because if the subway is 8, your local commute should be less than 8, right? So let's just say 3 right now. And again, I'm writing science fiction, okay? But you will write a science fiction several times until you feel comfortable with it. Okay? So I don't like the number, too small. Let's use 5. Okay. Yeah, that's better. How big did I get? Oh, too big. Let me use 4. Compromise. This got nothing to do with my math, okay? It got more to do with when I'm teaching it, easier to see. Okay. Lock the number, paste value. Why I lock the number? Because if you don't lock the number, every time you hit return or something, it keeps changing. So just lock the number. So now we fake our data. We're done. So where the address of each one of them? ADD, address, and so we'll see the address. Some of you, I know, that love to bring your own computer, and I do one step, you do one step, follow all the way. Just listen to it, okay? If you copy paste too much, sometimes your brain is not really thinking. You only just copy paste. Okay, so if I sum and say that every location Depends on, hey, how much local commune, how much this commune, how much relative to the central station, I'll get the number. And here is the number. And this number is the observation. If we run the 16 trial experiment, this is what we're supposed to get. But remember, we're not really running an experiment here, right? We're just saying that if you run the experiment basically says that there's an overall average. And then there are some treatment very, very good, some treatment very, very bad, so there will be 11. And then on top of the design, there's a little bit of local fluctuation. So overall, some very, very good, some very, very bad, some local fluctuation, you end up with your observation. See that? Okay? So we get that done. Now, let's do the opposite way, what we did last time. So here is our observation. And remember, you don't give this observation 1, 2, 3, 4, 5, 6, 7, 8, follow the sequence. Should be randomized. Why? Because it's not fair if it's not randomized. Okay, so once we have that, what we do? First, find the central station. How we find a central station? How do we find a central station?
Average.
Average of how many?
All of them?
Average, Senorita, here, in green, yeah.
Is it all?
Good. Sometimes I ask a question, it's not because I don't like you, it's I need confirmation that we're on the same page. Okay, so, what did I do? Oh, I need to lock the number. Yep. So first things we already see. Here is the deduction. The deduction means that we start from some assumption. The assumption is start from 101, but when you using the statistics going backward, it's called induction. And obviously our inductions based on the 16 number, our estimation of where is the central station, good or bad?
Pretty close.
I'll say pretty good. You know why? 16 observations, try to figure out that number. Of course it's not too bad. Okay, now let's figure out the local station. Okay, so, well, before we do that, we need to calculate the sum of square of the total. So sum of square of the total. This time I'm lazy. I'm not going to do it. I'm going to do a sum difference. Huh? There should be a sum difference somewhere. Okay, let's try it again. They don't have it? Sum square, sum total. Sum x plus, oh, probably this one. Well, let's double check. I'll do it once and then I'll if it's still there. Oh, there it, hold on. Sum return total sum of square of number of two, return sum of total, no, that's plus. Between differences, okay, that's the one, okay. So what will be the differences is this guy and this guy. Okay? And one more. Remember at the end we have the Pythagorean theorem to double check we got the right number. And, you know, if I made any mistakes at the end, my double check will tell me. So I don't care. Okay? And then next, the local station. So subway estimate, same thing. Yeah?
Can you check that SS total? Is that the same thing if you do like the sum square?
Yeah, oh, you mean like what I did last time?
Yeah, so.
Okay, sure. Well, sure. But I'm trying to say that there should be exactly the same, but let me just do it once to, okay, let me do it here because I don't really need it. So I will do this. Equal to this guy minus this guy. Or the other way around. Well, it doesn't matter. Because we're going to square them, so positive and negative doesn't matter, right? So, but if I do this, okay, and sum square, okay, happy?
Thank you.
Good. Next. So let's measure the subway distance. So the subway distance equal to the average of what? The average of what? The average of this four, right? So we'll have this four. Need to lock this time I need to lock only the row. Okay, so 113 above 100, 89 below 100, yada yada. Okay, so this time we'll have a sum of square, but this sum of square is the treatment sum of square. So let's just say sum of square treatment. And what is the sum of square treatment? Should be the sum, the things, right? Minus, yeah, differences. So this time I'm not going to do the differences again. I'm just using it. Using this 4 minus this 4. Okay? Because here, no matter where you live, you always travel from 113 to 100. No matter where you live, you use subway station D always from 89 to 100. No matter where you live, if you're using ZZ, the ZZ will be always this much. Agree? Huh? Okay, yeah. So now you see why I use this funky subway station travel. It's easy for you to see that. Okay, so this is a treatment travel. Okay, finally, the local travel.
How did you find the subway, the last table you just did?
Oh,
Yes, that one.
remember what I said? Hey, we all travel, just for all travel using AA. And where is the AA location? The average of those four, right? So the average of everything, the average of local. Okay, so let me go back to this guy. The overall, the subway, same. See that? Okay. Okay, so now we need to calculate the sum of square of the error term. So the sum of square of the error term is what?
The sum of square of the total minus the sum of square of the treatment.
Sorry, I didn't hear you. Should be what? Everybody minus the subway station, right? Should be sum minus here we go. Okay, of where I am, where my substation at, right? That is the travel. So now is the time to check our wonderful Pythagorean theorem. The sum. No, we don't need to do sum, just, hey, this guy plus this guy, we get this guy. Right? Okay, so now Pythagorean theorem is true, and then I can say percentage-wise, right now, my treatment sum of square is about 95%, ridiculously good. Okay? And I don't like that. Let me destroy this experiment. Let us have the treatment so bad that is below 70%. How to do that? So in other words, if you actually have an experiment like this for your senior design or for your capstone projects, tears in my eyes. Okay, should have been better. Okay, but let's make it really terrible. Below 75. How to do that? Okay, so.
Go back to the end, please. Will you slow down, please, just a little bit?
Okay, but cannot be too much. Because you have the video too.
I know, but I want to understand it.
Okay. Yeah. Go? Okay. So now, in order to make them bad, how to make them bad?
Increase the error.
Increase the error? That's one way of it. Okay, we'll do it your way. So, increase the error is having the random number of here, okay, norm, IMV, norm, IMV, okay, and then I have a random number for probability, and then the mean still 0, but let me have a variation, let's say 15. 15 is terrible. Why? Because the subway is 15, right? And what I'm doing, okay, say my subway station here is 15, right? And then my local commute is way above 15, way below 15. In other words, is that if you look at this chart, look, the local commute is supposed to be around here, right? But if I have a bell shape, giant, that means what? Hey, I live below the subway station, way below. And then what? I drive all the way up, even passing the central station, and say, I don't want to come down. I need to go all the way to the subway station I want to be, and then take the subway. In short, that's stupid, right? You go all the way, passing where you want to be, and then coming down. Or you go down all the way, and then take the subway. Doesn't make sense. Agree? So, we do it her way, right? Because we want to destroy everything. So, if we have this, and then we say 15. Okay? And, yeah, we can do that. And you guys see what happened? Our sum of square error looks so huge. Your treatment becomes relatively small. And once you do that, the proportion you left is 24%. Right? Can you see that? Okay, that's one way out. But that's not the only way out. So let me keep my 95% for a second. What's the other way out? How about changing this 101 to 42? The cyclic number of the world, of the universe, right? The hitchhiker of the universe? Yeah. Not too many people know what I'm talking about. We got generations. Okay. So how many of you think that if I change the number to 25 will help us? Change 101 to 25, would that, when I lower the central station location, will help? How many of you think that will help? How many of you think that that doesn't make any difference? Well, imagine this, okay? Now I don't want to sacrifice my paper. You got a piece of paper? Okay, people, imagine this. Can you see it? I have a central station and two subway stations in some local community. Can you see it? Okay. Now, the location of my central station is 101. I calculate the subway square, the distance, everything, relative to 101. I say, I don't want 101. I want to drop to 42. I drop to 42. Everything dropped was the 42, from 101 to 42. But the relative local commute distance and the local subway station, does it change because I lower the level? No, because they're relative to the central station. So what if I said, I don't like 101, I want to move to infinity and beyond? Everything will move to infinity and beyond. The local community commute will relative to the, say, 1 billion whatever number. You guys follow me? Because we did every computation. Well, let's try it to see is to believe. Okay, so I moved the number to 42. Does it change anything? I just moved the center station to 42. Doesn't make any difference, right? You see that? Because it's relative to nothing. Okay, so obviously changing the location of central station is not the way out. What else can we do?
Change the distances.
Yeah, you can change this. Okay, now they're stretching, right? What if, okay, I make them, say I make this guy's, yeah, I I can make this guy 5. And this guy's 3. And this guy's -2. This guy's -4. Still, oh, I cannot do this one. This one needs to be balanced. So it is the negative sum of those. Okay. Does it make any difference? Drop to 69%. Okay. Now, regurgitation time. Think about it. What have I done? And what does it mean? You two, want to share your jokes? No? Okay. What have you learned so far? You can consider this is a big pizza or big pie. It's 100% of the pie. Okay? And the error term, okay, needs to be what? Needs to be locked at a certain level, but you want to make sure that there are some error term left. And because here, if I don't have the error term, okay, can you make decision on, when I said that, oh, my subway station, my treatments make sense, is a logical treatment. Do you have anything to compare with if this is 0? No. So you need something to compare with. Okay. So error term is always important. Okay. It's almost like the yin and yang sticks in the Asian and Chinese philosophy. In order to see the sunlight, you need something to block the sun so you can see the shadow. Okay. Okay, so step 1, we create a average, sum of square, and everything. And once you create that, okay, let me go back to my original one. Okay, let me leave it right here for a second. Now we can build our ANOVA table. The ANOVA table always have the sum of square column, and the sum of square at the beginning we only have treatment and error. Okay, and then of course when you add them up together, it's total. Okay? And the treatment sum of square error, sum of square term is equal to this guy. And error is equal to this guy. And then the total should equal to this plus this. And next things we need to talk about is degrees of freedom. DOF. Degrees of freedom. Anybody heard that terms before? Okay. And what is degrees of freedom?
It's been a while since I've heard that.
Well,
I remember.
Well, this like central limit theorem, I don't want you to memorize some Wikipedia definition. Because if you memorize it, you'll forget it. I want you to learn through thinking. Okay? Anybody want to give a shot? What's degrees of freedom?
No, thank you.
No, thank you. Okay. If I have an object in space, one dot. How many of you got robotic or mechanical engineering background? How many of you MBA background? So you must take robotic or dynamics, right? So a dot in space, how many degrees of freedom? Huh?
360.
Only 3?
360.
Right?
It's more than the
No, there's 360 is one plane.
Yeah.
No, what I'm saying is that anything in space, in a 3D space, has 6 degrees of freedom. Why 6 degrees? X, Y, Z. And then alpha, beta, gamma. Okay? So, degrees of freedom means how many ways I can move it around. Okay? So, actually for me, when I talk about the average, I'm really trying to explain to you, it's almost like center of mass. Right? I'm using the balance to explain that. The way to think about degrees of freedom is almost like thinking about that kind of constraint or that kind of meaning. So I think right now I have like 8 or 9 students. Here I have probably 30 or 25. I don't care. Let's just say we have 20 students. Okay? So say I'm interested in your age. Okay? And I want to know your age. And of course, one way to do that is what? Ask everybody, subject 1, subject 2, or student 1, student 2. So I have a student number. Okay? And for every student, I ask you, hey, tell me how old are you? So the student can say that, I'm 32, I'm 12, I'm 18. Nobody laugh. Okay? But when I ask you how old are you, give me your age, right? Before I ask you, okay, that observation can be what? Anywhere. Just like I have 16 number, right? Before I ask you where you live, okay? Before I ask you where is your address, your location is a random number, right? Could be anywhere. And once I ask you, I basically said that, oh, that's your number, I'll lock you down. So people, watch this. Okay? I have 20 students. Before I ask you how old, and you tell me how old, how many degrees of freedom I have? I have 20 degrees of freedom. But every time when I ask you a number, you give me a number, the log. However, I said that registrar office just told me the average age, listen to me carefully, the average age of your class of DoE is 22.4. Okay? If I know the average of this is 22.4, and I still would like to know everybody's age, how many times do you think I need to ask? How many of you think I still need to ask 20 times to figure out everybody? Huh? How many times do I need to ask?
19.
Why 19? Because average is sum of the total divided by n, right? Divided by 20. So, in other words, it's this. If this is 20.4, the total of this classroom should be what? This number times 20, right? It's 448. If I know the total of this sum together is 448, how many do I need to ask? How many? 19. Just like when I did here, remember what I said? I know where is my central station, So some trouble above, some trouble below. The fourth subway station, the last subway station, always equal to the sum of the other three. Why? Otherwise, they won't equal to zero. As such. Okay? So, what is degrees of freedom? Degrees of freedom, you can think about it. Remember this one more time, okay? If someone asks you in the job interview, if you're looking for data mining, machine learning, whatever jobs, okay, if you want to get a job at Triangle Park, work for some pharmaceutical company, you know, develop COVID-25 vaccine, okay? They probably will ask you, okay, so what is degrees of freedom statistically? You can think about it. The opposite. What is degrees of freedom really is the constraint. Because if I said the average is this, that means what? I add a constraint. So my degrees of freedom lose one. If I add another thing, I'll lose another one, which is independent. So you can think about it. Degrees of freedom means the degrees of freedom, you know, without those constraints or with those constraints. Follow me? So degrees of freedom, here, I have a robot. I can move like this. I can move like this. I can do a lot of things. But if I have some impedance to say that, hey, you know, say a little kid riding a bicycle, you're helping the little kid. You're grabbing the bike from the back. So the bicycle cannot wobble this way or that way. It can only move that way. The boy moves what? The degrees of freedom, because you add the constraint, right? So same things. Here, we're adding the constraint. Oh boy. Online student going to complain because they cannot hear me. Hello? Okay. So let's do it. So the degrees of freedom, okay? The total, do we average the overall average, the central station location? Yes. So the total degrees of freedom is what? 16 minus 1. We only have 15 degrees of freedom. Same thing. For each subway station, we need to figure out their average. But we have 4 subway stations. We're supposed to have 4 degrees of freedom. But the last one is logged by the other 3. So it is 4 minus 1. So the difference is whatever left for the error term is equal to 15 minus 3. Is 12. And once you have that, now you have the sum of square. You have the degrees of freedom. You can figure out the MS. Okay? And the average of that equal to this guy divided by this guy. And this guy divided by this guy. And now we can calculate our F statistics. Okay? The F statistics really in this case is how much on average for the 3 subway station the commute sum of square gonna be divided by the local commute gonna be, and the number is 78.38. Okay? And this is the magic number we're gonna compare with something and say that, oh, that 78.38 is beyond reasonable doubt. It's very significant. Or I have quite some doubt. It's not that significant. Okay? So, this is a point, if you take it from some math professor that would say, let's look at the textbook using the back of the textbook. And for me, I would like to explain to you how to get the F statistics. Step one, last time I already told you how to get a normal distribution. A normal distribution is what? By taking a bunch of random number from any distribution, so we can just use uniform distribution, and then take the average of, well, I'll do it one more time.
We can't see that number on the screen.
Oh, okay.
It's a little too far over to the left.
If you start at like E, you can see it. It's small screen.
Start from E?
Yeah.
Okay. I won't want to do that because I'm not going to remember. Okay. Okay, let's just start from A. Okay, and let me move to A, B, 10,000. Okay, and now let me lock the random number. Paste special value. And once I do that, I lock the number. And of course, you want to have a perfect shape. You should have as many as possible, as many to take the average as possible. So 10,000 maybe not good enough. Maybe 1 million would be good. Huh? Oh. Let's just use average. Okay? And I think I already true to you last time. If you use the histogram, you will see a very nice looking histogram of this guy. Okay? And so if you look at this, if this is the central limit theorem, says that where is the bell shape coming from? The bell shape is coming from the average. So let me do the opposite to prove that average is the good one to have to have that. So let's say using the mean or the max, or you can use quantile, 10% or 20% of the 30 observations. Let me just use the largest number and the smallest number because it looks fun. Okay, so rather than taking the average, I'm taking the smallest number, or I'm taking the biggest number of a bunch of random number. Okay? And if I'm looking at the max and then do a histogram, okay, and guess what you guys gonna see? The histogram gonna look like this. Why? It's not centered anymore. It's, hey, give me the biggest one you can. So it's pushed to the right. So if I'm using the smallest number, the mean, to build the histogram, what do you think you're going to see? Is pushing towards zero. So you guys see? What I'm trying to show you is this. If we're using the average. The number is everywhere, right? But now it's pulled toward the center. If I'm using the max, hey, give me the largest in your sample, or pushing to the right. If I'm saying, give me the mean, we're pushing to the left. So when you will get a nice looking bell shape, it's when you take the average. So if I take the average, I'll get the number. That is your z-score number, that's your normal distribution. Okay? And the normal distribution, mathematically, okay, is expressed as the following. Okay? Let me go to here. Okay? The normal distribution, generally speaking, it should look like this. Okay? Well, let me use standardized normal. Okay? If I start from -4 and this number minus 0.1, plus 0.1. Okay. And now you know that the distribution of this should look like what? The z-score should give you, let me just plot it. Okay, so is 1 over square root of 2 times pi okay, and then divided by exponential half of the z-score square and this 2 together will give you the height of the PDF function. So if you do this, okay, and you plot it mathematically, insert this guy is fine. Okay, if you move here, this is the theoretical normal distribution should look like. And of course, this is from our central limit theorem. And if you have a lot of number, sooner or later, since there are enough number, this guy will look as smooth as this theoretical shape. And for those of you who say, hey, I don't remember my teacher did anything, and just go to Wikipedia. Okay. Normal distribution. And this is the equation I just used. And for standardized normal, what will be the sigma? 1, right? And square root of 2 pi, 1 over x minus mu. Inside, that's the z-score square. Okay? And so, homework for any of you don't remember anything of that, at least fake a couple, just plug and play. For different mu, for different sigma, you will generate different bell shape. Easy, right? Okay, so if I generate a bell shape, and then different bell shape, basically said what? See the green bell? Start early, so the transfer function from 0 to 1 start early. Look at the orange one, is expand for a long time, it will transfer, expand for a long time. So for those that are in my reliability class, I always said that PDF is a mountain, CDF is a transfer function from 0 to 1. Okay, that is the same view from Bayesian frequency, whatever class I'm teaching. That's the way how I see the world. A mountain turned into a CDF. So let me do that just for fun. Okay, so how to turn a PDF into a CDF. Okay, step 1, let's turn them into percentage. Okay, so I'll say percentage or PDF. Okay, so we need to turn the mountain into a transfer function, right? From 0 to 1 to a CDF. How many of you ever done that before, other than in my class? How many of you remember the teacher say something about PDF turning to CDF? Yeah. Okay. So, you want to do it?
No. They showed me how to do it in the calculator.
No, I don't want you to use calculator. I want you to do it freehand. So, the first thing, double check, okay? Remember how many number we have? 10,000, right? So we just sum everybody together. Okay, I'm lazy, so I didn't lock the bin. You know, technically you should lock the bin into some specific number. I'm just letting your Excel decide. Okay, so I have 10,000 number. First thing first is everybody, every histograms bar divided by 10,000. Because once you do that, what will be the sum here? What will be the sum of all the percentage together?
It'll be 100.
Huh? 100
100.
or 1, right?
Yeah.
Okay, so if this whole thing is 101, so now let's do some integrations. So the integration is start from nada and gradually moving up. So we just call this the CDF based on the percentage approximation, right? So what I will start is I'll insert from 0. Hey, I start from nothing. Now add a first bar. Now add a second bar. Now add a third bar. So every time is whatever I had before, add what I just increased. So add increase, add increase, add increase. So by the end, I should move to 1. And if I move from that to that is 1, then I know my transfer function from nothing, add a little bit until I'm reaching 1. That is your transfer function. Okay? And of course, you can say that here, when a number is very, very low, how likely I'm in there? Not very likely. More likely, more likely, more likely in there. Okay? That is our CDF. And in this case, we basically said that when the value is 0.1, 0.2, how likely that belong to the bell? Not very likely. Okay? And of course, you can just look at this end. You can also say when this number is getting too big, it's not likely. So that basically says that there is a range. Something should look right. Okay? And if you want to look at that, okay, Excel, rather than doing my way, they just said that, okay, if this is my z-score, okay, -4, how many of you are Lean Six Sigma fan? You know, getting a green belt, yellow belt, black belt, whatever belt?
This is the plan, I haven't started yet.
Yeah. So Lean Six Sigma, why Lean Six Sigma?
So Six Sigma is essentially defects per million opportunities, right? So
Uh-huh.
Six Sigma means that the number of defects that you have per million is so small. It's the standard deviation, right?
Yeah.
The Sigma standard deviation.
So bell shape basically said what? +1 -1 sigma is 66.6%. ±2 sigma is 95%. 3 sigma is 99.9 something percent. So you know that, okay, if your control is so tight, your bell shape is so under control, how likely you will have a number flowing out there? Not very, very likely, right? So that's where this z-score can be abused. So now let's just say that rather than using here, you guys agree with me? I just come up with a average and everything's here, right? So what if, okay, I want to build here, let me go back to this. Where's my 3? Okay. So if I want to find the sample I have, and it just says that the average of the average, where are you? Okay? The average of average is 0.49, it's almost 0.5. Make sense? Because we're using, yeah. Then the standard deviation is about what have I done? STD, standard deviation. From here to here. Okay, and the standard deviation is 0.05, okay? And 0.5, it's easy to remember, even though I'm just using approximation. So people watch this. No, this one. Where's number 5? No, where's number 4? Here we go. Okay, so here is the location of the bin, right? So rather than using the location of the bin, okay, if I have every bin location, I said, hey, give me a z-score of that. All I need to do is using what? This, let me copy paste that number so it looks accurate. So this is the mean, and here is the standard deviation. So let me just copy and use that. Paste special value. Okay, so every score, how to calculate a z-score? Minus the mean divided by a standard deviation, right? Yeah, if you don't remember what the z-score really normal distribution, just think about it. It's always minus the mean divided by the scale, the standard deviation. And once you do that, okay, log. Okay, then we get a z-score. And then we said that, hey, give me a normal distribution, standard normal distribution based on the z-score. Okay? And then you'll get a number. And now, if we compare, first let me just finish it. Okay? So, now I have two different way to get to the number, the CDF. This is, accumulate, accumulate, accumulate. This one is based on the normal inverse. Basically, the Excel give me the distribution probability. Let me just move these guys over here so we can see them side by side. Okay? So, this one is the simulated one. We sample. This one is the theoretical one. Okay, one is theory, one is sample. And if you compare the two, let me have two bar charts, see how close they are. The blue one is the theory. The red one is, I just, stack together. Okay, without using any chi-square or goodness of fit, would you say that central limit theorem and the theoretical distribution look pretty much the same? Yeah, okay. Okay, so why I'm doing this is to convince you that z-score can be a bell shape. Now, what is chi-square? Because the steps I need to get into is the chi-square. Okay? So, to get into the chi-square, let's do this. Suppose that I have one z-score squared, z-score, and I squared them. Okay, I've just summed one z-score. So let me just have a bunch of z-score. So I just have a bunch of norm S I N V. Okay. So here is basically I generate a normal distribution, one z-score. Okay, and if let me just make a few. I need a 3 and a 15. So let me make a 3. Okay, let me first go to B, D 10,000. One more time. Control C, D 10,000. Okay. So, people, if okay, I ask you cannot see it. Shoot. If I ask you to plot the histogram of B column, that's one bell shape. I ask you to plot the C column, is another bell shape. The E column is another bell shape. But no, D column is another bell shape. But basically, I can't prove to you I can build a bell shape based on random number. Agree? But now you just say that don't bother, sample a bunch of stuff. Let Excel do it for us. So I have one bell shape, two bell shape, three bell shape, histogram ready. So if, okay, I'm just doing sum, square of two random number. Okay? That means what? I'm adding two bell-shaped square together. if I have 3 bell-shaped square, I can say sum square of 3 random number together. And of course, I can have some square of 20, 30 random number together. And the more you sample, okay, what do you think that, okay, so I said you're not allowed to be negative, okay, you're always using the square. You have to, whatever, say you're a bell shape, but you have to square yourself, so you always report to me the positive. You're doing the same thing, you're doing the same thing, so nobody allowed to tell me the other side, always using the square. So even your bell shape says negative 2, 1. You just say that, oh, square of 2, 1, give me a positive number. So every random number of bell shape only allowed to give me positive. Okay? So now I can say, hey, I only collect 1 square, I only collect 2 square, I only collect 15 square. What do you think the more I collect, okay, and when I build the histogram of this sum of a bunch of squares, what do you think will happen to the distribution? Will it spread out more, or will it be tighter and tighter? Huh? Why I squared them? Once I squared them, every number is only spread. So the more you add, the more you're going to spread. Let me prove that to you. So suppose that, now let me just use 1 square, okay? 1 d² square. Okay, so I have 2 versions. The first one is only using 1 number, 1 square. This one using 3 square. Okay, and let me lock the number. Control C, paste special value. Okay, so if I'm using 1 square versus using 3 square, okay, and then let me go to G 10,000. Okay, now let's first compare the histogram of using only 1 square. Data analysis, histogram. Okay. Oh. Okay. So look at this bell shape. Not bell shape. This chi-square, okay, was 1. So it's not bell shape anymore because I squared it. So look how it looks like. Oops. It just spread this much. But if I use 3 of them, okay? So data analysis. Histogram. Okay? And look at a shape. Let me use this one. So compare this one with this one. This is only 1 z² square. Yeah? Okay. This one is 3 z² square. Can you see that when you have only one, it's kind of like very close, not spreading out. When you add 3, it's spread out a little more. If I have 50 or 60, it will spread out even more. Okay? So, why we want to talk about this is for the following reason. When we build our ANOVA table, okay? When we build our ANOVA table, remember I have some error term. The error term is what? A bunch of square, right? Divided by the average, right? So the more square I have, naturally they could spread some out more. So right now I'm saying, hey, this is what I see from my experiment. But compare this opportunity. How likely this spread is spread far, far enough beyond this random spread. So I'm trying to say that, so what is random spread? So that's why I start using normal distribution. Because the normal distribution is basically the court ask the statistician, beyond reasonable doubt, what the heck is reasonable doubt? As a statistician, you need to say, based on central limit theorem, this is as far as I can spread. And this thing spread beyond the natural spread by this far. I don't think this is natural. This must be something else. You guys follow me? So right now, I'm getting closer. But the only things that I need to do is show you what is reasonable doubt, how to build a yardstick. Okay? But I want to show you how we come up with our observation. Okay? I will come up with the problems next time. Okay.